All right, welcome guys to the second part of the 2.1 video notes. So we're going to finish this page here today. Shouldn't take too long. And again, as always, if you have questions, please feel free to email me, send me a message, do what you need to do. Make sure you understand this. So this whole page is going to be about location. And I told you last time that we want to create standardized curves, right? Most famously the bell curve, right? So then we can compare different scores under the same distribution. It's essentially what we're trying to do. So we have a problem here. So Macy is a 3-year-old female who's 100 centimeters tall. Brody, her 12-year-old brother, is 158 centimeters tall. Obviously, Brody is taller than Macy, but who is taller relatively speaking? That is relative to the other kids of the same ages, who is taller. According to the CDC, the heights of 3-year-old females has a mean of 94.5 and a standard deviation of 4. The mean height of 12-year-old males is 149 with a standard deviation of 9. Okay, so I'm going to give you an equation here that's going to be the most important equation that we have. So we have z equals x minus x bar divided by standard deviation. Okay, and this right here is called a standardized process. So z is a standardized curve, and so we're going to use this formula here to figure out which one of these people are out of Macy and Brody who's going to be taller relative to their age group. So I'll do this in two colors. Let's do Macy first. So Macy. So Macy is a female who is 100 centimeters tall. That becomes our x. So we have z equals 100 minus the mean, which was, according to the CDC, they have a height of 94.5. Divided by the standard deviation of 4. Okay, so now we're just going to our calculator. And if you type this all out, you get z equals, and I guess technically this is in parentheses to the top part first. You have 1.375. So that's for z score. And now let's do Brody. Now we have Brody's z score. And so he is 158 centimeters tall. So we have z equals 158 minus the mean height here is 149 divided by the standard deviation of 9. Okay. Let me write a couple things here on the side. So this symbol, sigma, stands for standard deviation. And let me do one other thing here. To be technically correct, this is actually, I'm going to erase this and make it a mu. Okay. Now, when you go through this, you're like, okay, well, what's the difference between mu? Just stands for the average, okay? And you're going to learn in a couple chapters that mu and x bar are different things. Whenever you see a Greek symbol, you're going to be looking at a population parameter, versus if you are looking at you're looking at an alphanumeric values like x bar, which uses our traditional alphabet, is going to be a sample. Okay, that's kind of where we're going with this. So again, Greek letters means population, alphanumeric means sample. But that's just some minor details for right now. So anyway, back to our problem here. So we're going to simplify this down. So z equals, if you simplify this down again, this top part is technically in parentheses, is 1. Okay. So now what this means is that because Macy had a higher Z value, had a higher Z score than Brody, Macy was actually taller in comparison to the rest of her group. Okay? And so to explain this a little bit more, I'm going to clear these drawings. Okay? So when you look at the normal distribution, you have your bell curve. Looks something like this. Right? And you have your mean go smack dab in the middle. So here is what we call mu. Okay, this weird looking U thing. Okay, and what you look at is this is now a standardized curve, and so what you're looking at is your distance away from the mean, and so your z-score is a measure of that distance away from the mean, okay, which is what the next question is going to talk about. But essentially, you have positive z-scores going this way. You have negative z-scores going this way. Okay, so the more extreme your answer is, the more extreme the probability is going to be, right? So if you have a value way out here, right, that percentile is going to be extremely high. Same thing if you have a value, I can actually write this, so like a probability out here is going to be like, it's going to be really high. So high, this is going to be a high percentile. And then if I have a value on the other side, it's going to be the opposite of that, which is a low percentile, right? So it's kind of where we're going with all this. And it's kind of why that's why Macy is taller in comparison to her brother. Okay, so that's kind of the idea behind this, right? We're trying to put everything onto one curve, and then we're going to measure that curve by the distance away from the mean. That distance away from the mean is measured in z-scores, okay, which is the number of deviations, and then we're going to get into all that in a little bit. So scrolling down. So this is kind of what I just said. So put some text here. So z-scores are measured in the number of standard deviations away from the mean. So in other words, z-score tells you the distance from the mean. And I gave you the equation earlier. I'm going to write it again. So we have z equals x minus mu. I'm going to write two equations here, divided by sigma. So this is for your population. And if you don't have that information, you can go z equals x minus x bar divided by s. Okay. So the difference between these two right now, so this is your sample. So the difference between these two right now is not the most important. We're going to get into more of this as we go out through the course. But for right now, just know that z is equal to the x value minus the mean divided by standard deviation. Okay, that's the big thing to take away from this. So this is the big thing to take away from this. Okay, so this right here, and know that that z-scores are just a measure of distance, just a measure of distance away from the mean. Okay, so we're looking at a couple different home run hitters. We got Barry Bonds, Roger Mathis, Mark McGwire, Babe Ruth. And we want to figure out how they did in comparison to the rest of their group, right? So for each one of these, we've got the mean for their given year, the year that they broke the record, and we want to say, okay, in comparison to everyone else in that year, right, who did the best? Because as you can tell, between 1927 and 2001, we're hitting more home runs, right? So on average, we're hitting a lot more home runs between 1927 and 2001. So did Barry Bonds do significantly or relatively better when he hit 73 home runs compared to Babe Ruth when he hit 60 with a mean of only 7.2, right? So that's essentially what we're trying to do. Trying to compare these distributions. So we can do this a couple ways. So the first one, so Babe Ruth is going to equal 60, so that's your x, minus 7.2, parentheses, divided by 9.7, which is your standard deviation, and that is 5.44. Okay. Now we have Roger Maris. Okay. Similar type of, so we need the same equation over and over again, right? We're standardizing this onto one curve. So 61 minus 18.8 divided by 13.4. Yeah, I'll put some parentheses in here to make it look a little more clear. And this is equal to 3.14. Okay, these different colors. And now we have Mark McGwire. And I'm going to do the same thing over and over again. Again, we have Mark McGwire's individual value, X, which is 70. He hit 70 home runs, minus the mean, which is 20.7, divided by the standard deviation, which is 12.7. That gives you a value of 3.88. And then last but not least, we have Barry Bonds, who hit 73 home runs, minus the mean, which was 21.4, divided by the standard deviation, which is 13.2. And that equals 3.91. Okay. So now, based on our definition of the z-scores, we have a bunch of z-scores here. Okay. So we have Mark McGwire's right here. So we're going to compare all these values. We have Babe Ruth, Roger Maris, Mark McGwire's 3.88, and Barry Bonds 3.91. So now out of these, we're just going to be the furthest away from the mean, right? Again, z-scores are just a measure of distance. So in terms of distance, 5.44 is going to be the furthest. So we can see that Babe Ruth based on relative averages, Babe Ruth performed the best when compared to others in his year, right? He had the highest z-score value. Okay. So now, eventually what we're going to get to in this unit is talking about how to find percentiles for these things. Okay. So now, all we want to do is just look at location. That's all z-scores are, measure location. So we know that Babe Ruth did hit the most amount of home runs in comparison to did the best compared to everyone else in that year. Okay, last question for this video. So this is going to be a similar one, but this time what we're saying is we've got a z-score. We're going to give you the z-score. This is like working backwards. We're going to give you the z-score, and we want to figure out and calculate the number of home runs hit. Okay. So we know that our equation is z equals x minus the mean, x bar, divided by standard deviation. Okay, and we know that the z value here is negative 0.48, so I can put that in. So we have negative 0.48. Right, so here's my, so I'm just gonna put this z value in right here. Is equal to x, which is what we're trying to solve, because x is the number of home runs we hit, minus the mean, which in 2001 the mean was 21.4. Okay, I just took that from the chart. Divided by the standard deviation, which again I just took from the chart. You can look at the Barry-Bonds row, which is 13.2. And now this is just a matter of algebraic manipulation, right? We're just trying to solve for x. So go back to your algebra 1 days, your algebra 2 days, right? Multiply by 13.2 on both sides. Okay, these are going to cancel out. 13.2. Now, before I finish this problem, I want you to think, and just think about this to yourself, have a little intuition about it, right? We have a negative z-score. So are the number of home runs that Mark Grace hit going to be higher or lower than 21.4, right? That's a good self-check to yourself if you understand what this is, what this z-score concept is, right? Because I'm going to give you some random z-score, okay? Do you know that, can you just make it an estimation or a guess about what x is going to be, right? And the answer to that is, well, it's a negative z-score, so that's going to be below the mean. And if it's below the mean, then I know that x is going to be less than 21.4, right? So just kind of have that intuition. It's going to be really good. So anyway, when you multiply that out, you get negative 6.886. I like using 3 decimals just for accuracy, but 2 is fine as well. So x minus 21.4, right? Add 21.4 on both sides. Hopefully this part isn't too difficult. These cancel out, and you get x is 15.06 home runs, 0.64 home runs, which is approximately 15. And again, I'm going to label my answers because in this class, that's the big thing, is we're interpreting these values. Okay, so now if I wanted to write a quick little sentence about this is the last thing, right? We can say with a standardized score of negative 0.48, Mark Grace will hit approximately 15 home runs based on the data for the year 2001. Okay. I guess it's past tense, so it hit approximately 15 home runs based on the data from 2001. So that's just an introduction into z-scores. It's a brief introduction into some percentile stuff. And now the next step is going to be, we're going to talk about transforming data, and then eventually we're going to talk about coming up with actual percentiles for each of these things. So there's going to be a table that we're going to be looking at. That's going to be coming up in the next couple of videos. So as always, if you have any questions, please let me know. Shoot me an email, whatever it is. But if not, have a great rest of your day.